All right, welcome back, everyone. We are here with another programming challenge. I've got a slightly new setup here, so this is also going to be a little bit of a test run to check if my how good my new setup is for these programming challenges. So the programming challenge is it's here on the left. Good morning. Here's your coding interview problem for today. This problem was asked by Etsy. Given a sorted array converted into a height balanced binary search tree. Okay, so let's start by defining the terms. So sort array, right? So I'm assuming it's a one-dimensional array, and it's gonna have like some numbers in it, or something that's comparable, right? So we'll assume numbers now for simplicity, but it could be strings as long as it implements some sort of comparable interface. We can probably do the same thing. So it's something like this, right? And the values are already sorted, right? So like this. Convert it into a height balanced binary search tree. So I have a guess as to what this means. This I'm not familiar with this precise terminology, but I can make a guess of what it means. So binary tree, binary search tree in particular, means it's a tree such that whenever you have a node, it has like up to two children. It could have zero children if it's a leaf. It could have one child or two children. The subtree to the left, every value in the subtree to the left is smaller than quote unquote this node, and every subtree to the right is bigger than this node. So I'm doing a little picture here, a picture representation. So a version of this tree, there are multiple trees, binary search trees you can construct to represent the data in this array. Let's see, 1 and 2. Okay, so it would have to be something like this is one possibility, and then there wouldn't be a node here. So this is a binary search tree of the above data, but you could also have it be like this, right? Where would 4 be? 4 would be on this side, and then actually, let's say 5 is here, which would mean 4 would be like here-ish, right? And then 1 would be from both to here, and I'm running out of room on my ASCII art, but the idea hopefully is relatively clear to people who have some programming familiarity. So for every time you have a node, every value in the subtree to the left is smaller than this value, and every value to the right is smaller, is bigger, sorry, than the value in this node. So that's the binary search tree part. So what about height balance? Height balance, I think what they mean by that is the height is as small as it possibly can be. So like this tree has a height of 2, right? Like 1, 2, or maybe 3. I don't know if you count this guy, but it could be smaller, because what I could have done is let me think, how could I have done this? Oh no, maybe this is the minimal tree that you can do. Maybe, okay, so I might need more numbers to make the point more explicitly. So let's say I had 6, 7, 8 at the end, and then I'll put 7 over here, and then I'll say 6 is to the left of this, oops, and then 8 is to the right of this. So this has a height of 4, right? 1, 2, 3, 4, but it could have a height of 3, I believe. And the way you would do that is, I'll leave this tree here for comparison. You will want to put one of the middle values near the top. So let's say we'll put 5 here, and then you have this subtree and this subtree that you want to appear on the left and right respectively, and you just recursively say I want one of the middle values. So let's say I put 2 here. So then 1 would be on this side. I need 3 and 4 to be somewhere around here. So let's say, oops. Let's say 3. Let's say 4. Am I already? Did I already mess up? Could I have made this smaller? If I put 3 up here, no. Interesting. I'm sure there's a counterexample, but I can't seem to construct it. What if I just say there is no 4? If there was no 4, then this tree would look like this. The thing is, I'm confident in my answer. It's just I'm not coming up with a good example to illustrate what I'm trying to say. That because all these challenges are always done blind, so I don't get to prepare ahead of time. So sometimes my examples don't work out if I'm just making it, like I say, I'll just try making a random tree as an example, and then the random tree doesn't have the properties that I'm trying to demonstrate. Yeah, I think, okay. So this tree has a height of 3, right? 1, 2, 3, when it's balanced. And when it's unbalanced, in this case, let me just make sure I have all the data here. 1, 2, 3. We skip 4, 5, 6, 7, 8. Yeah. So this tree has a height of 4. This has a height of 3. So I think height balance just means you want the height to be as small as possible. And like where balance comes in is the idea that in order to make the height as small as possible, you want the left side and the right side to be approximately equal sized. Sometimes you can't, because like if you have an even number of entries, like when I had the 4 over here, you have to pick some element to be the middle element, right? Like 5, for example, and then the left side has 4 elements, and then the right side has 3 elements, and that can force one side to have a different height than the other side. But in general, if you get them approximately the same size, that's what's going to give you the minimum height tree. So I believe that's what they mean by a height balanced binary search tree. And the reason like you want that, the reason this is a nice property to have is that then when you try to actually use a search tree to search for a value, you have an upper bound on how many checks you have to do, right? Because if, like, as you guys probably know, to actually use your binary search tree, you start at the top, and then you say, like, let's say I want to check if 7 is a value in my tree. So I look at the top as a 3. Okay, so I know 7, if it's present at all, would have to be on the right-hand side because all the values on the left are smaller. So I go down here, and then I know it's bigger than 5, so I'd have to go to the right. So I go here, and then I find it. If you have like an arbitrary long height, then you might have to look at an arbitrary large number of nodes, right? But if you have a very short tree, that like the height of the tree is the upper bound on how many nodes you have to look at to check if the value you're searching for is in the tree. Yeah, okay, so that's all the background information to make sure we actually understand the question. So now let's talk about how do we actually solve the question, right? Like now that we've understood the question, what's the solution to the question? And I mean, I sort of solved it in pseudocode or like, when I was giving the example. The idea is, since it's sorted, intuitively, you want to pick some value in the middle, make that be your top node, and then you recursively say, now I want to make the tree with the smallest height on the left and the tree with the smallest height on the right, and put that on the left and on the right respectively. I don't know if that's proven to give the optimal results. I'm a bit hand wavy there, because what I'm thinking is, like, let's say there was a 4 here. So now there's there's an even number of nodes. So it's unclear if when I say pick the middle, should I pick 4 to be at the top or should I pick 5 to be at the top, right? I have to make a choice there. And depending on which choice I make, this side or this side might have a slightly higher height. And then when I recurse onto here, then I have to make these subtrees, like maybe this side is going to be higher and this side. And so like it's not completely clear what the final height is going to be. So it's not a rigorous proof that this heuristic of saying, okay, just pick something from the middle and then recursively do the left and right is guaranteed to give you the optimal shortest tree. So I'm wondering, is there a different algorithm that I can do that does guarantee the absolute shortest tree? So I'm intuitively, we know the shape of all the optimal trees, right? Like we know that a tree of size 0, looks like this, the empty tree. We know a tree with 1 node is going to look like this, basically. We know that the optimal tree with 3 nodes is going to look like this, right? Like you always have the middle value here, and you're always going to have the smaller value here and the second smallest value here. Even if, like, here I'm using these as indices now into the array rather than the actual values in the array. I'm saying this, like if you have an array of size 3, it's always a second index element that's going to be here. Like I'm doing 1 base counting here because I'm using natural English to describe my solution. You're always going to have the second index here, the first index here, and the third index here. And we know for like, I guess, I don't know how many nodes this is going to be. 3, 4, 5. No, wait, this is gonna be 6, 5, and 7. We know for arrays of size up to 7, it's always gonna be shaped like this, again, based on, these are the indices, not the values. So I'm wondering if we can use that to guarantee this height balance property globally. Because right now I was only guaranteeing at each iteration step, but if I do like the wrong thing, because I was hand waving with the previous solution, the property might not be preserved over recursion, and then the global height might not be optimal, even if the local height is optimal. Okay, so if I do this, like, is there a general algorithm for constructing the index like this? If there is, I don't know it by heart. I'd have to rederive it. I'm guessing there is. I mean, because like, I can do it like as a human, right? I just got to figure out what the pattern is. Oh, I think it's always okay. I think it's always going to be a subtree, right? Because we said before, this is the size 1, this is the size 3, this is the size 7, and then what I mean by that is each solution uses the previous solution as a subtree of itself. So then I guess this would be 8. And you would have 9 here, 10 here, 11 here, 12, 13, 14, 15. Is this right? Let me check here. The symmetry is a little off, so I think if I put leading 0, the symmetry will be better. I mean, graphically, the graphical symmetry. The logical symmetry is still preserved. But in the ASCII art, it's not being preserved because I'm not drawing it properly. And if I draw it like this is going to be 0, 4. Just going to be positioned here, and 0, 8 here. Then yeah, I think... Yeah, we definitely have a structure going on here. So the key is to figure out how do I compute the structure? So it's always like a power of 2 minus 1, right? So this is, I guess I'll put, how can I notate this? So this is like 2 to the 1 minus 1, equals 1, size 1. This is 2 to the 2 minus 1 equals 3. It's 2 to the, oops, wrong symbol. 2 to the 3 minus 1 equals 7. And this is 2 to the 4 minus 1 equals 15. So that gets us started. So I guess when I have the array, the first thing I want to do is I want to take its size, right? And then I want to do like the log base 2 of the size of the array. Maybe if the array plus 1, something like this. So the idea is, like, if I have an array of size 15, for example, I want to get 4 as my answer, right? I'm trying to figure out this exponent here. And if you give me an array of size 7, I want to get 3 as my answer. So you give me 7, an array of size 7, I add 1 to it to get 8, and then I take the log base 2 of 8, and I get 3, right? That's what I'm going for here. So that tells me, like, if we use this number here as the index of this list, like I have a list where this is the first tree, this is the second tree, right? It's shaped like this. This is the third tree that's shaped like this. I can figure out like which tree in the list of this infinite list it is that we want, and then I can construct that tree. Okay, so let's say now I know this number, right? So we have 2 to the n minus 1. We're going to construct a tree of size 2 to the n minus 1. And we've calculated n by doing this, right? We take the size of the array, add 1, and then we take the log base 2 of it. So we're trying to build this tree. How do we do that? So we use recursion, right? So given that I know how to build given that I can build this tree to build this tree, I just all I have to do is I build this tree. The notation is a little weird here. I build this tree twice and then put a middle node on at the top. Right? What I mean by so here, this, let's say I want to build the 2 to the 3 tree, and I already know how to build the 2 to the 2 tree. So I build the 2 to the 2 tree once, so that's this part here. I build it again, which is this part here, and then I put a middle node at the top, right? So if I do that, then I will have constructed the tree. So I can use recursion to build all these trees. The only thing is, like, so when I say build a tree, I have to give, I guess, a starting index, and that's going to determine the ending index. And I guess I can figure out the ending index by doing this formula, right? Like, the ending index on this tree is or let me do this example so I don't have to keep saying 3 over and over again. The ending index of this tree is 7 because 2 to the power 3 minus 1 is equal to 7. So I know it goes from 1 to 7. I can now make the starting index parameter, right? So I say use 1 as the starting index. It's going to go up to 7 for the size 3 tree, and then I say, okay, build that once. Sorry, I think there's some dust in my mouth, so it's not moving properly. So I'm not going to point with stuff with the mouse while I try to clean it, but I'll keep talking. So I build the left subtree, passing in, saying the starting, use 1 as your starting index, or 0, maybe depending on the language. Probably 0 because most programming languages use a base 0 indexing. But we can fiddle with the +1s and -1s after when we write the unit test to make sure our solutions work. But yeah, so build this tree with starting index 1, and what's going to happen is it's going to build this node, this node, this node, this node, this node, this node, this node. Because of the formula, we know the ending index is 7, so we know the middle node is going to be 8 here, and then I can say now build this subtree with starting index 9, right? Not with starting index 1. So I said, okay, start at 9, so it builds this, and then using the formula again, we can calculate that it's 15. How do we calculate that it's 15? I guess you know the starting index is 9. You add the size to get 16, and you do -1 because we started counting at 1 instead of starting at counting at 0. So yeah, there will be a bunch of +1s and -1s, the off by 1 errors that we'll have to figure out. But it shouldn't be a big problem. Okay, so I think that's basically it. And the thing is, once we have the index, then it's easy, right? Like, if I know that the first index 1 goes here, index 2 goes here, index 3 goes here, and so on, then as I build the tree, I can just reference the values in the array and then put them in. So I think that basically solves it. Okay, so now that's the the pseudocode. Let's actually turn this into code. So I got my wheel of languages here. Let's spin it and see what programming language we're gonna do it in. I'm pretty rusty in a lot of these languages. I'm using more or less the same list that I used before, and I'm hoping I get a friendly language. Oh, good, JavaScript. I'm pretty strong in JavaScript, I think. Like, I've been using JavaScript recently. So this should be relatively easy. Okay, so how are we going to do this? I got let's go into the JavaScript directory. Oops, that's the Java directory. The JavaScript. And there's my hello world. How do I run? I use Node, right? I say Node. Yeah, okay. So let's open up this hello file in here. And so the idea is we're gonna have a function. Let me see this thing again. What is it called? So I'll call it sorted array to balance 3. And you pass in the array. Let's make the font a little bit smaller here. Actually, let's just make this full screen. Okay. And what are going to be our test cases? I guess I don't want to set up a whole what's it called? Like testing framework here. So I'm just gonna use immediately invocable functions, right? Immediately invocable function expressions to basically have like scope, like basically small pieces of code that I can use and then throw away. Like all the entire environment is thrown away. So any local variables I declare or whatever. So like I'm gonna do a test case where, okay, let's say I give it the empty array. What do I expect as the output? I'm gonna use const actually. I'm gonna sorted array const result sorted array given this, and then how do I do assertions in JavaScript? How do I do it? Let me think about how do I do a tree even. I guess I'm just gonna use like JSON objects, right? Like, so I'm gonna object equality is by identity or something like that, right? I can't do a deep equals. Okay, so this is actually gonna be annoying to do. So instead of doing unit tests, I'm probably gonna do like manual inspection tests. The thing is, I don't want to sub like Mocha and all that stuff because that's a lot of boilerplate that I don't want to get into. So what I'll do is I'll do a function that just displays a tree to the console, and then we can just visually inspect it to see if it makes sense. But that's just gonna be a little bit of work too. So how do we display a tree? So probably the easiest way is, first of all, I'm gonna define what the tree structure is gonna look like, right? I'm gonna say a tree looks like probably like this. Like the value, I don't know if it's gonna be valid value. I don't remember value. Value is like a keyword in Java or JavaScript or not. Then we say left is, this is the empty tree, right is val5 f, right, something like that, right? So that's what the structures, that's the data structure that I'm going to use to represent all of this. And then for UI wise, I guess what I'll do is, so I'm going to say this is the input, excuse me, and then the output is going to be something like this. Let me think. I'm going to use like the old DOS style tree directories. So left is empty. I don't know if I'll actually print out the word empty or not. And then right is gonna have a 5, which then has empty and empty. Something like this. I think maybe a UI like this is probably good enough. Okay, so how will I implement this one? So I probably want another like an internal print tree that takes a like what prefix should I print in front of the tree, then the tree. And then the implementation of the main method is just to call my secret function with an empty string as prefix. I actually like to put single quotes for, I like to use double quotes for like human readable strings and then empty quotes for computational strings. I don't know what to describe. The idea is like, then if you want to internationalize the code, you can always search for the, you know, you only need to translate the double quote strings, and you should not translate the empty, the single quote strings. So to print a tree, what do? I print out the prefix followed by tree.val. Then on the next line, I print tree and the prefix is going to be the old prefix plus, let's see. Oops, I read the old plus like this, I guess. No, plus this. And then tree.left. Tree.right, something like that. And actually, I guess then this is where that dash comes in. And if this is only if there is a value. If it's empty, then we just, I guess we print out the word empty. I guess that's what we'll do. Prefix space, and then okay, so let's test if our print tree function works. I'll just do it here. Let's make this the fake tree. And then we'll do print tree, oops, on the fake tree. Did I call it hello? Did I just edit hello? Let's put a space here. This is good. I'm trying to. I'm looking at it. I'm like, something looks weird. The first empty and the 5 aren't lined up for some reason, but they were earlier. What? How did I mess that up? Oh, because I didn't put space here. I have to put space in both of them. Okay, yeah. Oh, interesting. But then I have the thing extend past the 5. Is that fixable? What if I do this? Does that fix it? Kind of. That's good enough. This is just for debugging anyway. This isn't part of the solution. Okay, so now we can see or look at our trees. So now the idea is like print tree. Test case, and then the array. So actually, I'm probably going to do a function that test case, because we're going to be manually or visually inspecting all of these guys. And so we're saying one test case is the empty tree, right? The empty array should give the empty tree. Right now, it doesn't do that. But and in fact, I think this will crash now because I think I'll do tree.val and it'll say there's nothing defined for val. Yeah, can I read property of undefined reading val? Yeah, exactly. Okay. Okay, so I think we've got our so-called testing structure ready, and now we can actually implement it. So what did we say? How did we say we're going to do this? So we're going to give it an array. We're going to find the tree index, right? What I mean by tree index is like, this is tree number 1, this is tree number 2, and so on. So I want to find that. And so we said it was array size. What all you gotta do is you take the array size, you add 1 to it. You do. How do I do? Let me. I'm gonna have to Google what math functions JavaScript has. JavaScript logarithm. Math.log. What does this do? Does it do natural log, I guess? Yeah. Okay. Okay. So we just do math.log of this divided by math.log of 2. And then we probably want to do like a math.ceiling floor? Probably ceiling. And let me just do some test cases of this, just to check if this is working. Bit tree index up here. Actually, I put the test next to the function it's testing. Next, okay, so we want. I'm trying to think of the best way to do this. Let me just do it like this. Okay, so if it's 0, then we want the tree index to return 0, right? And if it's 1, want 1. Oops, 5 to 11. 3, we want 2. Let's see, 4, 8, 7, and then 15 is what I'll do. All right, let's see what output we get. 1, 2, 3, 4. Yeah, looks like it works. Okay, once we know what tree index we want to do, we want a function that generates that tree, right? So we want to give the start index and then the tree index, like, is it tree number 1, tree number 2, or and so on. And then what else? I guess we pass in the array from which we're going to copy the values. Actually, let's do that at the end. For now, I'm just going to magically make the arrays, entries be 1, 2, 3, 4, 5, or equivalently, I'm going to have the tree just have the, what's it called? The indices here, and then at the end we'll change this to actually copy the values over. Okay, so how do I do this? So if tree index is less than 0, that's basically an error. How do I throw exceptions? Do I just do throw and then tree index must be greater than 0? That was whatever tree index was. Otherwise, if the index equals 0, and we just return what val is. No, I guess the notation, if I want to be consistent with this, right, is the notation is we just return this. This is the empty tree. X equals 1, then we return val start index, left is empty, right is empty. And then otherwise, now we're at a tree index is some n. So we do const left sub tree equals tree with the same start index, but with a smaller tree index. Mid. Let me think about this. Get tree size. I need a function that does the opposite of this, basically. So you give it a tree index, and it tells you how many nodes are going to be in that tree. So let me check. So if you say 2, it tells you 3. If you say 3, it gives you 7. Okay, so it's this formula. It's 2 to the power. This math.power or something like that. 2 to the tree index minus 1. Let me just do a quick test of that one. Temporarily, don't do this. Console.log, get tree size. Give it a tree index. So we say 0, 1, 2, 3, 4. 1, 2, 3, 4. Let's see what it gives. Ooh, that's not good. Did I? Oh, I didn't actually return the value. I just computed. Okay, there we go. 13750. I believe that's correct. 13715. 13750. Yep, that looks good. Okay. Mid index is going to be start index plus, and then again we'll check if there's a plus like on off by one error that we need to deal with here, but it's going to be the start index plus the get tree size of whatever our tree index is. No, of our tree index minus 1. Then the right subtree is going to be generate tree, where start index is the mid index plus 1. Right? That looks good. And so let's double check that. Generate tree with let's say a start index of 0 and tree index 4, I guess. And we're gonna do tree. I guess I'll put that after this declaration on here. Print tree, the result of generate tree of 0 and 4. I have a license for Sublime version 2 or 3. I don't remember. What are we at now? I haven't, I gotta upgrade my license. I purchased Sublime for version 2 or 3, and now they're at version 3 or 4. I forget which one it is. So I gotta upgrade my license. What do we got here? Oh, we got the bug. Can I read, which is line 59? Really? Generate tree. Oh, did I not return? I didn't actually return the tree. Okay, and then the tree itself is going to be val mid index left subtree right subtree. Okay, that should be good. This does not look right. Let me. So the 7 here is good, but then the 19 here is messed up. 1, 2. Is this generate 3? Yeah. Then you got 4, and then this should have been 5 somewhere. Am I reusing a shared variable somewhere or something like that? Is that my mistake? Oh, is it? Maybe I don't want const. Maybe I want let. Is const like a static constant? I thought it was a constant local to this. Yeah, I'm pretty sure it is a constant local to this. Wait, why do I have plus start index twice here? That's probably the bug. That's right. It probably has nothing to do with const. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, this looks good, right? Although, shouldn't have served 0? Why did it serve 1? I guess I have an off by 1 error somewhere. Maybe it should be -1. Because I think I'm counting. What do I say as a size? Tree size 0. What is the size of tree size? It should be 0, right? Tree size 0 is 0. Yeah, okay. So tree size is correct. This thing is not correct. Why is this not correct? So if I say, oh, did I say start? I said start index 0, right? Yeah, start index 0 with height 4. Eventually it's going to get to tree size 1. In which case I do this magic thing. Tree size 1 should have height 1, or size 1, I mean. Which it does. And so it should have put the start index as 0 there. Why did that not work? Is it this +1? There's no way this +1 is wrong. Wow, I'm so confused why I don't have a 0 in here. Oops, did I not save? Yeah, so I'm trying to generate 304. Hang on, let me put a few more debugging statements. I'm just trying to debug what's going on here. Let's just log this thing. Zero 04, 03, 02, 01, index 1. 1, left, right, 0, 1, 2. That looks good. So what happens to it? Left 0, 1, 2, 3, 4, 5, 6. That looks good too. 9, 18, 15, 11. Yeah, that looks good. Okay, that looks good. So this should have descended into something, right? I guess the print tree has a bug in it. On the node that says 1. Oh, because 0 is a falsy value. Gosh darn it, this freaking JavaScript and it's falsy. Okay. Where's print tree? Tree goes undefined, I guess. Did I mess up? Or is it just null? Let me think here. No, so there, okay, I gotta think here. Tree is false. So if, sorry, if 3 is truthy, or 3 is specifically 0. I'm too lazy to look up what exactly. Yeah, now we have the 0 in there. Exactly how to do the fix the falsiness with JavaScript. What is it breaking on? Line 64? Oops. Print tree is failing? I feel like this is getting a little hacky now, where I'm like, I'm not sure what's going wrong, and I'm just doing bandage fix to fix everything. But this works. What was it failing before? Oh wow, I'll figure it out later. Okay, so this is good now. We don't need these debugging statements anymore. As you can see, I'm not an expert at JavaScript. And then I guess that's to be expected. If I'm doing the wheel of language thing, I don't get to choose what language I'm programming in. So sometimes I get lucky with a language. I'm fairly familiar with JavaScript, but not in the like I don't remember all the library functions. I think they're like, how do you check for undefined? I don't know if undefined is like NaN, where undefined is not equal to undefined or something like that. I think it is, but then it's unclear to me why what I had before didn't work, because I thought I was checking like if it's undefined and stop recursing down into here. But anyway, Okay, so where are we at? We built the tree. I think we're almost done, right? We built this tree. So all we need to do now is yeah, I don't even need this function anymore because generate tree basically does it. All I need to do now is you give me the array. No, okay, I do want that. Well, let me think about that. Yeah, let me undo so I bring this function back because I think I do want this function because I like this. This is the easy to use API that the client probably wants to use. But it'll basically be just a call into this function. So now you give me an array also. And when you give me the array, now that I have the index, instead of putting the index as the val, I'm gonna just index into the array. I think it's just this. I think if I do this, then we're good. And then okay, so then how do I get the size of an array? Is it array.length? Array.size? I don't remember. But I'm gonna get the tree index. Where's my function? Here it is. We'll try length, and if it doesn't work, we'll try size. So we get the tree index, and then we just return generate tree. Start index is 0, tree index is what we just computed, and the array is the array that we were given. And so, actually, let me do this. So we don't have this anymore. But we still have show test case. So let's see if this works. Yeah, so then A, B, C, C, D. We take 4, 8, so I want 7. So this is 5, 6, 7. And I want 15 or something like that. 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we want some things that are like not exactly the right powers of 2 or whatever. Let's try it just like this. Cannot read property if undefined, reading 0. What does that mean? Oh, did I pass in a string or something like that as array instead of passing in an array? Where would I have done that? Show test case is I give it an array. Show test calls this with the array. Here I have the array. I pass the array in here. Here's the array. Why is this wrong? Let me go back a bit and see if it still works with the index. Oh, because I forgot to... I know what the problem is here. I need to recursively pass in here. I wish... this is one of the reasons I like Stackly. Stackly type languages. Because it would have told me, hey, the number of arguments you gave here doesn't match the number of arguments you're expecting up here. But whatever. Okay, let's go up and ABC, that looks good. A, B, C, D, E, F, G, A, B, C, D, E, F, G. I think that's right. Let me just think here. D is the middle value that it chose, right? Yeah. D is the middle value, then it says B is the middle of this, yep. And then E, F, G, yep. That looks good. This guy, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, yep. And then now this guy who's slightly unbalanced. Oh, that's interesting. It put all, like, it put basically H here. Oh, but I is missing. That's a bug. A, B, C, D, E, F, G, H, and then we don't have an I. Am I always missing? No. In here, I have the last element is present. But here, I'm missing an element. Okay, so there's a bug for us to figure out here. Probably an off by one error somewhere. So let's debug specifically that test case. Actually, let's do a couple more test cases. Oops. That's my passwords. You guys weren't supposed to see that. Hopefully I'll edit that out before I upload to YouTube. Here's what I'm gonna do. I'm gonna add test cases for like 1 entry and 2 entries. Let's see if that works better. A is this, yep. B is this. That looks fine. B. Wait, I'm really confused. Like, if none of these miss the I, what's so special about this guy that the I is missing? All right, let's try with D. And then with E. And then with F. I'll skip these guys because I know these guys are all correct. A, B, C, D, and then this is empty. A, B, C, D, and then this is... Okay, so the 5 case replicates the same problem. Okay, so let's debug the 5 case. This is okay for now. So the tree isn't like super balanced, but I'll come back to that in a moment. Once I fix this bug. So what happened here? What was the process? Print 03 generate 0201 21 0 1 2. That looks fine. Then we're done with that. There's some early exits here that I'm missing the end for, I just realized. Let's do that. Wait, what happened? I don't see my outputs. Are we going into this case? Oh, I put the I put the Gonzo log after return. That's why. That's why I don't see those log statements. So yeah, so this builds the A, this builds the C. Then we're done with this, so we build the B with A1C. We build just the E and then undefined. That's interesting. Why did it generate undefined here? Oh, because it's looking past the end of the array. Interesting. Okay, I understand where the bug is. Oof. How do I fix that? Because this is a core problem in my algorithm that I didn't think about. Okay, I think to fix this, when I generate the tree, I say start index. Do I have to say the end? Do I want to pass in the end index as well? And then compute the tree, like a different tree index. It's not always going to be -1. This is very interesting. I think I should compute the tree index each time instead of passing it in here and then doing a -1 decrementation. Okay, so let's do that. So then I'll say the start index is here, and I guess you have to pass in the end index also. Generate tree. So do it like this. And then, is there anywhere else I use the array? Is it just these two methods? So I think I'm gonna make this function be an inner function to this one, because then I can have the R variable as a in my what's it called, closure. So I don't have to pass array here. It's just available. Is this, did I fix setup? Let's just run it as is and just see. No. What did I do wrong? Tree index is not defined. Alright, I forgot to actually put G3 index. What do I pass in? The size here, I guess? Yeah, right, that size. No, I want to pass in this case now I'm passing in my start index. Negative infinity. Wow, now I'm really, like, I changed my algorithm midway through and now things are really messed up. Okay, so now I'm gonna for some move this down here, and instead of doing this stuff, I'll say, how am I gonna do this? Let me think. If start index greater than or equal to n index, I'm just gonna return an empty tree. Otherwise, we're gonna compute the tree index. And if it's I guess if it's 0, I would also return in the empty tree here. This is now this. Oh, all of these have to change. All of these indices are different now. If it's 1, this looks fine. Otherwise, the left subtree, I want to figure out the mid index right off the bat. So let's just do math.floor of start index plus n index divided by 2. Maybe I want the ceiling. I think I always want at least one element in the left subtree. So then I say Then the left subtree is the start index up until the mid index. The right subtree is the mid index plus 1 up until the end index. Red value, this looks good. Okay, let's see if this works. A with 2 empties. Okay, yeah, I was trying to parse this part. This part looked a little weird to me, but it's just saying it's a no with A, and A is otherwise empty underneath. I think I want more spaces to make this clear in front of the horizontal bar. How many more spaces do I want? 1, 2. Let's put 2 more spaces. Maybe if I remove 1 from each of these, that'll help also. Yeah, okay, I think this is a lot clearer. Okay, so it's printing out the E at least, but this is definitely not balanced. So what's happening here? There's 5 elements. When there's 5 elements, I wanted to pick 0, 1, 2. I want to pick element. So I do want floor, I guess. So ceiling. Pick now has to do BA, and it just happens to pick that. Okay, so yeah, I guess it was an off by 1 error with floor versus ceiling. So now let's temporarily comment all of these out, and then just let's look at the overall results. Since I radically changed the algorithm, let's make sure all the old test cases also work. I think this is, yeah, this is a new var. So empty array, empty tree. Just A with 2 empty childs. A, B, yeah, that looks optimal. A, B, C, yeah, that looks good. Here, you would have to pick either the B or the C as your mid child, and then whichever one you pick, one of the sides is going to have a height of 2. So the total height is 3, which is what we see here. Here, it picked a C, B and an A, D. I think that's good. Here it should pick C as the midpoint, which it did, and then it's going to have a height of 2 on either side, which is fine. Here it could pick C or D as the midpoint, and then let's say it picks this, then this would have a height of 2, and this would have so it should have a height of 3 total, which it does. Nice. A, B, C, D, E, F. Yep. And here A, B, C, D. So it should pick D as the middle point, which it did. And then both sides is going to be a full tree with B and F as the midpoints, which is exactly what we see. Yep. This one I'm not going to do in my head, but just do a quick inspection to see if it makes sense. Okay, L, M, N, O. Yeah, that looks good. G, H, I. A, B, M, T, C, D. I feel like this could have been optimized a little bit, this section, but let me just check that H. Okay, could I have done better here? Let's see. Is E definitely the midpoint? 1, 2, 3, 4, 1. Yeah, E is definitely the midpoint. And then I have to do a height, like 4 nodes in this tree. I would have to pick somebody. Whoever I picked, then no, yeah, this is optimal. You can't do better than that. So I think that's it. I think that solves the problem. Trying to think what else, like, people want to do, if you're in an interview situation, people are like, okay, so what's the big O running time and all that stuff. Print tree is not part of the solution. That's just for debugging, right? So really, like, the question is, like, this is going to return some data structure. How long does it take to construct that data structure? There's no loops anywhere, right? We just do recursion. Yeah, so this is just for testing. Print tree is just for testing. So all the real code is here, here, and here. These three functions: get tree index, get tree size, sort array to balance tree. And this doesn't have any loops in it. It just has recursion. And recursion is always, I pick the midpoint, and then I look at the left half and the right half. So I think it's linear. I think we only look at each number once. Does that sound right? You have the array. I pick the midpoint, which I can do in constant time. And then I just run this recursive algorithm again on the left side and the right side. Yeah, so I think that's linear. Because I'm doing a constant time, like constant work. And then doing that as many times as there are entries in the array. Okay, so that's pretty good. I think it's very hard to beat linear. It might be possible. So whenever you have an algorithm that's faster than linear, it means the reason it's hard to beat linear is because it means you're not even looking at all the data. Right? If you're doing faster than linear, you're skipping some data. You don't have time to look at every piece of data if you're sublinear. But I feel like you have to look at every piece of data to construct a tree, because you have to copy the value out of the array and into the tree, right? Presumably. You know what would be interesting? Because now I'm questioning that assumption, right? Do you actually have to copy the data out of the array? Because you know how earlier we have, what we did is we just generated a tree with indices, right? So I could just generate the tree with indices, and then instead of copying the data out of the tree, you can look up, or sorry, instead of copying the data out of the array, you can just look up, you can get the index and then you look up in the array. So then there's no copying. And then you might say, well, but generating the tree still takes linear time, right? Like you have to do the same process. Like you do this recursive call where you pick the mid index and then you do it. You do the thing as many times as there are indices in the array. But what I'm thinking now is, but what if I do it lazily, right? What if you say, what if generate tree returns in constant time because it generates an empty lazy tree, and then when you look inside the tree, that's when it says, oh, I better, actually look at the array and figure out what to do. That is a very interesting thought. I don't think I'm going to do that for this example, but you might be able to do, like, the thing is, worst case, like big O wise, big O is always worst case. Big O, it's still linear, because in the worst case, your lazy tree has to actually generate the entire tree or whatever, and so that you can look at your thing. But it's a very interesting idea, I think. It's something for you guys to play with, maybe, as extra credit assignment. Try to generate the tree lazily. I think it's going to be like, I wouldn't want to do that in JavaScript because I would want to have some sort of like clearly defined API, right? Like I know JavaScript has classes now, so maybe we can do something with that. But like the fact that it's not statically type checked just bugs me. It's a personal preference thing. I like it when the compiler tells me if like I'm invoking a method with the wrong number of arguments, that sort of stuff. So I would like to do it in a more static language, but it'd be cool if I return like a tree object, right? And then you can see like, get value, get left, get right. And it lazily, like, because it can compute the mid index without I know what the mid index is without computing the left or the right subtree. So if you're saying like, well, so tell me what's in the root of the tree, I can tell you that right away without knowing what the left and the right subtree look like. And so you look at the mid index and you're like, oh no, my value is smaller than that. So then you say, well, give me the left subtree then. And then I lazily compute just one layer of the left subtree, right? Like I immediately generate the root node of the left subtree. So I tell you, okay, so here's the node there. I don't know what its left and right subtrees are, and so on. But yeah, anyway, so I'm starting to ramble now. I think that's gonna wrap it up. I gotta remember, to edit out or censor or something the part where I accidentally showed my password on screen. But otherwise, I think this video is good to go on YouTube. So thanks again, everyone, for watching, and hope you enjoyed this. And yeah, keep practicing your coding. Have fun.